Okay, good morning, everybody. Let's change the subject a little and go on to structure refinement. You already tried the server yesterday, and I assume by now most of you got the results back. So here I want to explain what is the background and what is the detail about this structure improvement. So pretty much we can refine any structure that is there out in the PDB data bank, but there is a catch. We can do this almost. So the important thing is that if you want to use this sort of real space improvement for your structure, which can include NMR, cryo-EM, or crystal structures, you want to use it at the earliest stage of the refinement. If you try there are lots of very powerful crystallographic refinement packages that people use. If you use them and then come to this server, you will gain something, but the gain would be minimum. The important thing is that you try this at the various stage of the refinement. So let me go over some of the details of this structure refinement. Pretty much all of you know that proteins have different shapes, and the shape defines the structure. And the function comes from the structure. So function follows from the structure, and our goal is to improve the experimental structures during or after usual refinement processes. It's often hard to crystallize the structure, especially if you have a larger structure. If the structure is small, it is rather easy to crystallize and get a very good resolution for your data, and then the model building is not difficult. But if your resolution is above 2 to 3, 4, then it's hard to refine and then get a good model. And especially this methodology will work. So this is kind of if you want to call it a Cinderella story, that we have this and then we try to get a better structure from the existing structure. So how do we do this? In order to come up with this methodology, we define a torsional and statistical potential, which is a new measure of the backbone quality. All of you are familiar with the Rama maps. This is an improvement to the existing Rama map that I will explain in a minute. Then, in order to move the dihedral angles, we need a move set, which is very important, as you will see. And then if we improve the backbone, then the side chains, even a small change on the backbone will cause the side chains to move out of the electron density, the experimental electron density. So then we need the last step to improve the overall structure. So just a quick overview of the Ramachandran map. You know that we have two angles, the psi, which is the C alpha C plane angle, and then the phi, which is the N C alpha angle. And it has been known for like 40, 50 years that there is a preference for these regions of the phi and psi. Ramachandran was the first person who come up with this, and this is due to steric and electrostatic interactions. So basically, we have four non-basins. We have the extended basin, which has the beta and the polyproline 2. We have alpha right and alpha left. And these are some of the structural samples of these four different regions. So this is a typical Ramachandran map. Actually, we generated this by just collecting all of the PDB entries below 0.9 angstrom resolution. These are very high resolution data, and you can see that pretty much we have these four regions. However, if you look at each specific amino acid, for example, if I look at alanine just by itself, this is everything, all 20 residues. If I look at alanine, you see that pretty much it does not have the alpha left. Or if I look at threonine, valine, or aspartic acid, they all have different Rama maps. Okay, so this is everything. So let's call this state 0. This would be the state 1. for each specific amino acid, we have a specific Rama map. Okay? So this is a final resolution of the Ramachandran map. And then you can go even beyond this. Here, what we have done is that we look at the neighbors. Let's say I have an alanine in the middle, and then I want to see what are its neighbors. If I put the neighbors as everything, I will get this whole Rama map for the alanine. However, if I specify the neighbors, if I restrict the neighbors to valine and E, then you can see that the Rama map shrinks by a lot. So these are cataloged from the PDB. We look at all of the entries in the PDB below 2.2 resolution, and based on that, we have come up with this nice website that you can go in, put in what you want as the neighbors, and it will give you the distribution of the Rama angles. Okay? So you can see that Rama maps, first of all, depends to the residue type and also depends to the neighbors. This is a very important distinction that many people do not include when they analyze the Rama maps. And you can see that the Rama maps is much smaller if you consider the neighbors. We also have another addition which include also the secondary structure. If you take into consideration the secondary structure of this triplet, that would also be limited, but in this case I consider all. AAA means all. So we call this TSP3. Based on these triplets, we have defined a torsional statistical potential, which is in simple-minded, is a logarithm of the frequency of each amino acid based on the chemical identity of the neighbors, and this is done for the resolutions below 2.2 angstrom. So this would be a statistical potential that we have defined using these triplets. And to just check the validity of these triplets, what I'm showing here, again, this below 0.9 angstrom resolution data, and these are color-coded by our TSP values. Blue means good TSP, lower potential. Red means high TSP. And as you can see that pretty much most of the high resolution angles have low TSP, or they are blue. So this matches very well with what is given in the PDB with a high resolution data below 1 angstrom. Another indication that this is a valid scoring function is that here what I'm showing is that we look at all of the PDB entries into the protein data bank with 5 angstrom resolution. And we marked all of them with their average TSP value. So what basically is doing is that we look at each residue and then give it a TSP value and then we average it. You can see that there is actually a nice correlation between the resolution and the TSP value. The lower the resolution, the better your TSP score, or lower TSP score, because we consider low the better. So this should confirm that this neighbor-dependent torsional angles is valid and matches to very high resolution data. Okay, so a protein with superficially good Rama map contains many poor dihedral angles. So what I would like to show you here is that if you look at, for example, this protein, you can see that this is a regular Rama map that is pretty much everybody uses. You can see that this has only a few outliers, just this one and this, and pretty much everything is inside. So if you give this to an experimental crystallographer, pretty much they would say, okay, this is good enough. I have only 2 out, and this is a very good for the deposition into PDB, and we can move on. However, if I score this with the TSP1, you can see that also this is good. TSP1 meaning that I consider only each specific amino acid Rama. You can see that this is quite good with the TSP1 scoring function. However, if I score this with TSP3, And this is a real protein. This is a membrane binding protein. You can see that there are many regions of the Rama map that are marked as poor, and only a few of them are marked as good. So even in a structure that is marked very well, this structure is deposited into PDV, you can see that it still has many poor regions. So the goal is to improve these poor regions and bring them to the good part of the Rama based on our scoring function, which is the TSP3. So the important thing that I would like you to know is that one size does not fit all, meaning that if you have TSP1 or if you have the general Rama, that does not necessarily mean that you have a good dihedral angles based on the fine resolution that we have defined. So how do we do this? So now we know the goal is that to move the angles to a better TSP3 scoring. So how do we do that? So the goal is to bring this inside and also improve it based on the TSP3. So one simple way would be to just to rotate it, a pivot move, as it is called in the crystallography, is that to just rotate it and bring it in. But if I do this, and actually this is an example, then I would make a large distortion in the structure. The RMSD would be very large if I just make this pivot move. So this is not feasible. Actually, what I'm showing here is that this is a folding trajectory. Our lab also works on folding, and pretty much in folding they use pivot moves. You can see that by a small change in the one dihedral angle, the whole structure actually moves away, and now it is folded. So single pivot moves introduce unphysically large displacements, so we cannot use just simple rotations. We cannot also MD moves because there are large barriers to overcome, and you need a very, very long trajectory to come up with this, or very long simulation. So how do we do this? This is the idea. Let's say I would like to bring this Valin 5 to this region. So I have this, so I would change its psi angle by minus 170 degrees. Okay? So this would be here. I have a peptide group that is flipped. I want to correct this. So I will bring this in by minus 170 degrees. You can see the distortion here. Okay? So the chain goes out on the other side. The idea is that if I make the same correction for the phi of the K6, the neighboring residue, like a crankshaft, so I move one, and then I move the neighbor in the opposite direction, then you can see that I can gain the very good peptide, and also the chain is still in the same position. Okay? However, there is a catch here, is that I can correct one side, but the other side, if I want to make also a phi movement for this Valin 5, I need to do the same thing for the other side. So hence comes the idea of the double crank moveset. So basically the idea is that we rotate a phi and psi for a given residue, and then we correct the neighbors in opposite direction. And doing so, we can recover a good dihedral angle and also maintain the secondary structure as good as possible. So basically, this is the setup as the double crank, the novel move set that we have come about to do this sort of movements. So here, the idea is that I would like to go from here to here. So I would first make a change in the phi space, this blue arrow here. Then I would make a change in the psi space for the neighbors, I plus 1 and I minus 1. And then if I add everything together, then I would get this residue to move to the allowed regions of the Rama map by keeping the secondary structure intact as much as possible. Okay? So we have put this together. We have two things. We have the TSP scoring, the way I explain it, and also this novel moveset to a Monte Carlo simulation. So the stage of the refinement, as you tried it yesterday when you went to the website. Basically, is a Monte Carlo algorithm that would try to optimize the energy function based on the TSP3, based on the overlap with the input model. We try to keep as close as possible to the starting structure. We have also in the same process, we would like to improve the hydrogen bonds. Another very important thing in the structures are the hydrogen bonds. If you have more hydrogen bonds in your secondary structure, that means that you have a better structure. And then also we want to prevent the clashes between the atoms. So this would be the stage 1 of the refinement. And when we do this, we remove the side chains. So pretty much we only work with the backbone. After that, we add the side chains. And as I told you, if you imagine this is my arm, if I rotate the arm even by a little, the side chain will go out of the density. So I need to correct for this rotation of the side chains out of the density. And what we have used is that we have used the modified version of the molecular dynamics flexible fitting developed in Shelton's group in Urbana. And we have used that, modify it, and we do the second stage of the refinement to move everything into the density. Any questions? Yes?
So, how well does this work for resolution of 3.2?
Well, we use our Rama Maps for our TSP3 for 2.2 because those are more certain values. But this works very fine, as I will explain, as I will show you some results for higher resolutions. So pretty much we use the 2.2 as our cutoff because anything above that we consider not as good. So we use this, and as I showed you that the lower TSP value, it gives you there is a nice correlation between the TSP and the resolution. So here, this was one of our very good successes. This was a structure that actually one of our colleagues, crystallographers, UChicago is very well known for crystallography. So this was a massive structure, about 4,000 residues. And if you pretty much crystallographers, the way they work is that after they do everything with their softwares, then they just sit in and move the residues one at a time, bring them to the Rama map, score it, look at the clashes, and then accept or reject. This would take a long time to be done just by hand. But this ran through a server. This was the starting structure. Again, red means bad regions, blue means good regions. You can see that the result is pretty much blue after going through our server. Here, some statistics. We start with the TSP of 2.9. This is the TSP3 average value. We gain a TSP of minus 0.2. The hydrogen bonds improved a lot. We gain about 600 hydrogen bonds. And then, as I briefly mentioned to you, that we have these R values that are very important for the crystallographers, that they would, when they deposit the structure, these are checked, and these are like a correlation values between the data, experimental data, and then the model they built. You can see that we almost stay the same R, but the important thing is the R free value. When you want to build a structure, you put 5%, 5 to 10% of your data aside, and then based on that, you build, based on the rest of the data, you build your structure, and then you check how good that 5% will fit into the density. That's a very important measure, and we always improve that. You can see that's about 2% lower than the starting value. And these are the regular Rama. We gained 4% on the preferred region. We got 4% better in the allow region, and we have slightly higher outliers, but this is much better for the preferred regions. Here is another example. This is a acetylcholine binding protein. And again, the same thing, the TSP improved a lot. The number of H bonds improved a lot. And again, the R-free dropped. And here we improved. The outliers also decreased by about 2%. This is the cytochrome B6F complex. This is very important structure in photosynthesis. to begin with, this was actually when they deposited, the resolution was 3 angstrom. So we improved this also by a lot, and you can see that especially in this case, we improved the preferred regions from 83 to 91. If you want to do this by manual work, this is going to take you a long time to finish this. Just a quick note that there is if you are familiar with the ion channels, it happens that in the channels, the helices have kinks that are important, for example, for the gating. The one question that came back to us is that, okay, if you improve the secondary structure and the backbones, what happens to the helices, for example, for the membrane helices that are important? Would you preserve the kinks or not? And you can see that these are the helices of the cytochrome B6 complex. This is before and this is after. And we pretty much improved, but also we kept the kinks. This is the overlay of the before and after. Another question that is important is that, okay, we move the dihedral angles, but would we get closer to the high resolution data? Let's say if I work on two structures that exist in two resolutions, one in high and one in low, and I start with the low resolution, would I go toward the high resolution data or not? And this is an example. This is the data for the HIV transcriptase, reverse transcriptase. This is the low resolution data. This is after top, and this is the high resolution data. And here what I'm showing is that the difference between before and after for the phi and psi. And you can see that after the top, in average, the angles move closer to the high resolution data. Okay. So this is, so far what I talked about was for crystallography. Another very important aspect of this work is application to the cryo-EM, where you have very low resolution for the data. Two examples that I'm showing here. This is the tobacco mosaic virus. This is the monomer. Here you can see that this is the whole filament. And if I run this through the server for the monomer, I will gain about twice H bonds. And also if I calculate the correlation map improves from 0.68 to 0.71. This is another example. This is the acetylcholine receptor that I will start with a TSP of 0.85, gaining a TSP of minus 2.3, lots of more H bonds, and also again the correlation improves. Taking this data, we apply this to the actin model. You have heard probably a lot in this workshop that one of the things that we are working on is the actin. So there are two different filament models available for actin. One is the ODA model, which is more stable during the MD, and then the other one is the NAMBA model, which has the better dihedral angles. There are two available actin filaments published today, and the monomers have different structures. So the question is that if these filaments having the same shape, would it be the stability would be dependent to the shape of these monomers or the fitting? So the idea is that if we improve the fitting for these two models, would they get close to each other or not? This is a work in progress, but I can show you some of the data. This is the NAMBA model that we started with this, and pretty much you can see we clean up the Rama. And then based on this, starting from the monomer, we built an octamer, okay? And then we added water, and then in this case, because this was a large structure, and we, for the previous data, when we do flexible fitting, we do not use water. But because this was a massive structure, and then if we allow the more movement with the equilibration in water, we thought that this would give us a better data. So we used this and then fitted everything to the large cryo-EM data available. Based on this, here's some comparison between the residues of the ODA model and the NAMBA model. Pretty much you can see that the changes we observed are in the exterior loops. Pretty much the rest of the structure stayed the same. These are color-coded based on the different parts of the structure. And this is the C-alpha RMSD. But the important thing that happened during this process is that refinement can improve interactions between and within subdomains of actin. Actin is divided to 4 subdomains colored in pink, cyan, ochre, and lime. And you can see that if I look at the hydrogen bonding network for these 4 domains, this is before and this is after the refinement. For example, if I look at in the subdomain 1, I gain lots of hydrogen bonds. The same thing for the this is between the subdomains. Here again, 81 goes to 113, 2 goes to 6. So pretty much this sort of refinement through the backbone improvement and then fitting into electron density can improve the hydrogen bonds. Here I'm showing another example based on this actin improvement, we built coarse grain models, and you can see that these coarse grain models, red is the ODA model, and then the green is the NAMBA model, and even the coarse grains are different. And based on these coarse grain models, we built a filament, and then now we are running simulations on the filaments based on this refined structure for both, and we would like to see what would be the differences we observe. Any questions so far? And I would like to finish by just going through another thing that was developed, which is kind of related to cryo-EM structures that developed in the Dr. Volk's group. And basically what we have is that we have the idea is that if you start with a monomer, and then if we can calculate the density map from this monomer, can we identify a coarse grain model from this envelope that it's generated from this atomistic structure? So the methodology that developed works like this, that basically we have, what they do is that it's called essential dynamics, is a real space coarse graining model called essential dynamics that would identify 375 coarse grain sites. And then based on this 375 coarse grain sites, then a space-based elastic network essential dynamics coarse grain method was used to define a 4th site coarse grain. And these 4 sites matches very well to what is obtained for a atomistic structure of the G-actin. You guys are already familiar with the website. We worked on it yesterday, and then you got all of your results back, I assume, by now, and then I will explain. It came back with an analysis page that I will explain in the afternoon. And to conclude is that TOP identifies and improves the torsional angles, increases the number of hydrogen bonds, and generally lowers the R factors, requires only a backbone trace. So this is applicable to NMR, cryo-EM. Even if you want to build a model, if you want to build a homology model, this can be used to improve your model. Saves time in manual refinement, and if there is a missing portion, this could also help to, if you build a missing portion, this can optimize your missing portion into your structure. And these are the acknowledgements. I would like to thank Dr. Fried and Dr. Sosnick and the Godzilla group. This is our cluster called Godzilla. And then for the Center for Multiscale Theory and Simulations for giving the opportunity to talk. Any questions? Yes.
Those hydrogen bonds that you showed compared to the game were there after the simulation? Did you run simulation and compare it?
Before and after, yes. So
now, what I mean is that if you did you try to run simulation with with a low TSP score and a high TSP score for the, you know what I mean?
no, can you?
No, what I'm saying is that if you take a proof structure
Uh-huh.
and you don't apply your method
Uh-huh.
and run multidynamics, and
Oh,
you
you
apply your method and run multidynamics.
Oh, your question is how much of the edge bonding improvement is due to the backbone refinement and how much is it due to the MD? I could say about 40% is from the backbone refinement, and then about 60% is from the molecular dynamics flexible fitting. That does a very good job to improve the hydrogen bonds. But we gain hydrogen bonds also through our backbone improvement because pretty much we include the hydrogens, the backbone hydrogen through our refinement. Good question. Yes. Yes. Well, for the cryo-EM, there is a density, okay? But for NMR, this is a work in progress that we are working right now, is that there are NMR restraints, like, yes, NOE and so on. So there are programs that, similar to this flexible fitting, that can be applied after the backbone improvement. So backbone improvement would be pretty much the same. And then we can use, and we are working to modify those softwares to fit or improved backbone into the NMR restraints. So the same idea, and then I would just mention that, like for example, when we use flexible fitting, we restrain the dihedral angles to a certain degree to not allow them to move away from the improved backbone. Same thing, we are doing the same for the NMR. We restrain the dihedral angles that we improve through the first stage, and then we try to fit it into the NMR restraints. Any other questions? Okay, thank you.